I don't think you trust in my self-righteous suicide. I cry and you just deserve to die. Hello everyone. Alright, so today, as I had mentioned on Wednesday, I am going to have another Saturday stream, although this is Sunday, you may say. It is true, I was busy last night, I didn't get home until late, so I didn't want to stream at a unopportune time, and also I didn't want to put bad content out because I would have been extremely tired. But I did, however, make some progress on the errors that were occurring with Jeffrey. So since the Wednesday stream, Jeffrey has been updated, and actually I had to restart the whole learning process for him because I've realized that the original learning he had done was corrupted by the errors I had in the code. So the whole situation was that the things he was doing were completely random, and they weren't being rewarded in the correct way. It was rewarding the wrong thing for something happening, basically. So I fixed the problem, I restarted it. There's still some errors where the program is crashing, but I'm slowly fixing all of those. And like in the Wednesday stream, this is only showing the driver program. This does not have the boss program, the parent program, or the child program running. So the AI is not learning at the moment, but we will be able to see some of the progress Jeffrey has made compared to the Wednesday stream. And like I said, the Wednesday stream was a different session of learning than this, but the room for progress for this session is much higher because he's being rewarded properly for it. The traits are being rewarded properly and are being read in correctly. So now the whole process of learning should be in the correct direction. I'm just gonna check to make sure the stream is up here. But while I'm doing that, I will continue to talk about Jeffrey here. So what I've noticed is that he's been a lot more active in terms of movement. Now, a lot of this has been the random chance movement of the fact that he's spinning around and then something happens and he moves forward, just happening to be pointing in an outward direction. Hopefully we'll be able to see that because it's been happening quite a lot. And then, but what tends to happen is when the objects are out in that variable light area, Jeffrey will make decisions based off of whether he knows what they are or not, and in doing that, he can change directions. Oh, it just crashed there. Like I said, there are some problems I have not fixed yet, but we'll get it running again. So I believe, yeah, okay, so it's back up running. So now we have a new scenario. We should see some different reactions. But like I was saying, when the objects are out in that variable space out in the darker light area, they flicker in terms of what information he's getting. So he can only see them a random amount of the times. So then some of his decisions are set up to go forward when he sees those objects and to turn when he doesn't know what they are. So what ends up happening is a somewhat curved pattern, which is it's interesting to see. And here we go. We get so he's turning in one situation and he's going forward in another situation. So it looks like he's making those decisions, but now the object is in light, so now he's only turning. So these are things that have been happening. Nothing specifically showing intelligence has happened, other than the fact that these newer, more complicated maneuvers have arisen due to the situational aspects of the environment. So for now, the whole program, the whole goal for at right now is to continue running Jeffrey as much as possible. I've gotten him to a point. I've gotten the programs in total to a point where they can run on their own for a while, which is nice because now I can leave and go do something, and Jeffrey can be learning the whole time. I don't have to sit here and babysit to make sure that the programs are still running. So that should be something to look forward to in the future. I'm just gonna let him run for a little bit here in the start, but then I'm gonna switch to the ball drop project, because the one problem that's still persisting, and I think it's a computer problem, is that the Pygame, which is the print to screen module I have, is really vulnerable when it comes to the CPU capping out. So when I end up using 100% of my computer's processing power, it pauses and then it no longer continues to print to the screen because the actual window itself crashes as opposed to the program. So I won't be able to bring up Paint or anything and draw while this is running because it will crash. So I want to make sure you guys have something AI wise to be viewing. So I'm hoping to get this processing capping out figured out, but I'm not sure that it will be anytime in the near future. I think it's just a matter of upgrading hardware. But until then, you will see the ball drop program for the majority of the stream on Saturdays, and on Wednesdays it will be more focused on Jeffrey because that is the current project. So yeah, we probably won't see anything specifically new until he dies here, but we'll wait it out and see what happens, and then after that we can move on to the bulk of the stream, which I will be talking about quantum entanglement. And I will warn you that I am not in any way an expert on this topic, so please, if you have any complaints or if you believe that my information is false, simply look up, get a resource or something and send it my way, and I will gladly take that into account and mention it the next time I can. So Jeffrey just reset, and he will probably make the decision here in a bit to go forward. We'll see if anything else specific happens, if he can put himself into a new environment, but odds are about the same thing will happen. I'm not sure though, but we'll see. So I have checked, the stream is looking fine online, so like I said, we'll wait and see if he can move again, and then after that I will put it to a commercial switch it up to the ball drop project, and then move on to talk about quantum entanglement. And I'm hoping to go somewhat in depth, but at the same time not talking too much about the overall mathematics of it, because I know I for one wouldn't be able to do it justice, and also it wouldn't really appeal to a large portion of the crowd. So yeah, he's moving in circles. Is he going to catch that in the light again? Yeah, alright. So we've seen what happens here. He can't really do anything else after this happens, because his battery is staying fairly constant and his health is going down at the same rate. So and the environment isn't changing. So what's nice about this is that if the AI were running, he's stuck in this environment, so the AI will learn more about this environment in order to help him either do better in this environment or move on to a new environment. So it's nice when it gets into these cycles, because he can get better and better at these specific environments so that eventually he can move out. Now, every time I have to restart the program, it changes up the environment, and eventually this won't be a problem. In the early stages, it is somewhat of a problem because he can't spend enough time in one area to get really good at being in that environment. But then over time he will build up an average intelligence in all environments, and then it won't matter what the starting environment is. He will be able to make smart decisions. Oh, these are all speculations, of course, but I would assume that they're going to follow these patterns just based off of how the AI worked in the ball drop. So the one thing I'm worried about is harmony. So I'm worried that the different instincts won't really add up to a greater whole. They will just be good on their own, and then I'm worried that he will, if it gets into a situation where the environment is switching fairly rapidly, Jeffrey won't really be successful, because he'll be switching back and forth between trying to do several different things. So we will see how that pans out as it occurs, but for now I will retire Jeffrey for the day, and I will move on to the bulk of the stream. So I'll play an ad here, and I'll try and get set up as it's playing. Alright, there we go. It says we're back. I'm just going to get the paint window up so I can have somewhere to draw. And then if you guys see anything wrong with the screen, just let me know. It's hard to tell what is missing on the edges when it is sent to YouTube, because the YouTube window is a little bit smaller than what's actually sent. So I will get paint up here, and there we go. Alright, so like I said, I will be talking about quantum entanglement, And so that may be a little daunting of a topic on the surface. So I hope to shed some light on the whole idea, because I feel as though a lot of people just assume that that topics like quantum mechanics and special relativity are way out of their spectrum of possible knowledge. And although there are aspects of those higher topics that are rather hard to grasp, the overall application and logic behind them is a little simpler than what people usually expect. And the way I always claim is for special relativity is that the concept is actually harder to grasp than the math. Now that's a little different with quantum mechanics because of the necessity of a idea of vector spaces, and this is a somewhat higher math concept, but I hope to give a general explanation of what it means to have of some more general quantum topics, and give you guys some ideas of what the whole area of the whole school of thought is. So the first thing that anyone learns in terms of quantum mechanics, and you may have heard of this already, is the whole Schrödinger's cat metaphor. So that is the idea that if you have this box here, and you have it's a three-dimensional box because boxes are voluminous, if that's a word. So there's a box here, and there's a cat in the box. And so what is significant about this is that you do not know what is going on inside the box until you open it. So this is a cat. I will warn the animal lovers, this is somewhat of a morbid metaphor, but it gets the job done. So there's this cat here, they call it Schrödinger's cat, and so when the cat is in the box, there's also a capsule in the box with a random timer on it that will randomly open and release gases killing the cat. Or it doesn't have to be a capsule, it can be any means of killing this cat. But the whole idea is that the time aspect of it is completely random. So it could be 1 millisecond, it could be 10 billion years. You have no idea when this capsule opens and kills this cat. So in terms of applying your knowledge about this box, until you open the box and see if the cat is alive or dead, you can't claim that it is either. So you have to make decisions based off of the fact that the cat here is in a superposition of alive and dead. So what a superposition means is that it is both alive and dead, or it is or you can think of it as any possible combination. So it's either alive or dead, but you don't know which one it is, so it's both. And that's a little hard to grasp, but it makes sense in how you apply it. So this could apply to a social topic in a sense. So let's say gender identity. There's a lot of talk about gender identity. So before you know what someone affiliates or how someone feels about gender, then you shouldn't act as if they are one specific until you comfortably understand what that person feels comfortable with. So this is the metaphor of Schrodinger's cat, and that explains superposition, which is not one static state, but a sort of a combination of the two states and the lack thereof. We see some superpositions coming into play in some, I believe it's chemical states. So if there's, not chemical states, chemical structures. So if you have a particle that is like this, and then it has a singular bond here and a double bond here, then the double bond could either be here or it could be on the other side, so then you have the same thing but it's mirrored, and these are both the same and have both the same probability of happening. So what happens is, when it comes to applying math to these structures, you have to imagine that they are constantly fluctuating between this state and this state. So you treat them as if they're in somewhere in between, where the bond length is slightly smaller than a single bond but slightly larger than a double bond. Now this isn't necessarily what people would normally consider as it could be technically quantum, but the scale of magnitude is not necessarily quantum in effect. So I'm gonna clear the slate here. So the idea of a quantum effect is when things get really small. So you have buildings, that's macro scale, so you got windows, and yeah, so you get it, dot, 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 dot. And then so that's macro scale, and then micro scale would be even smaller than that. You could say microorganisms are microscale. You could even go smaller, saying that a molecule is microscale. But then when you want to get quantum, you have to get to particles. So that's electrons. Electrons are one of the best examples of something that follows quantum mechanics. So when it comes to applying physics to an electron, you can't follow the normal Newtonian rules of F equals ma and all the Newton's laws. So the different rules that apply are the quantum mechanics. So I'm trying to think of where to start here. So the way that electrons work. So there's many different ways you can explain an electron. Electrons have mass. I believe that's some 9.11 times 10 to the negative 31. Someone can correct me on that if I'm wrong. And then they have an electrical charge, which is it's 1.6 times I think it's negative 12, maybe even more. So they have a decent charge, but their major effect is in numbers. And so electrons obviously play a count in electricity because it's flowing charge. But if you know anything about electricity and electrostatics and magnetism, is that when you have a moving charge, you get a magnetic field. So that's if so electrons, you can imagine them as a little particle, and the way that a lot of people will describe will add characteristic to an electron is they'll describe its spin. So you can imagine this little particle spinning around in circles in space, and the thing is, if you have a charge that is spinning, you can imagine it somewhat like having a circular wire. So here's your wire, and having a charge on that wire moving around in that circle. So what happens is when you have a circular a loop of wire with a charge moving around it with a current, or which is what a moving charge is, you get a magnetic field coming out of that ring. So magnetic fields work perpendicular to the direction of the charge, the direction of motion of the charge, and they curl. So there's a right hand rule. So if you hold up your right hand and you point your thumb in the direction of the charge, the direction of the motion of the charge, then you can curl the rest of your fingers, and that is how the magnetic field works. So it curls around the wire like that. So in this case, the electric field would be curling around the wire like this. But then if you think about the charge being over here, it's still moving in this direction around the wire, but in this instance it is moving down. So if you hold your right hand and point your thumb down, it's kind of an awkward angle to get your elbow that way, but you can see that your fingers will curl around this way. And so what happens is all of the magnetic field flows through, or the flux of the magnetic field is in this direction through the ring. And so what happens is, if you see a particle like this one and it's rotating and it has a charge, it basically is a infinite number of infinitesimally small rings of charge spinning around in circles. So what happens is, when you get a spin like this, what I'm showing here, then you can do your right hand rule, and what happens is the magnetic field it creates is downwards. So people in the scientific community would describe this particle, which we're saying is an electron just for simplicity's sake, would have a spin of down. Now the confusing part is the fact that so let's just imagine you had a ball. A ball doesn't always rotate around a vertical axis. A ball could rotate around a horizontal axis. It could rotate around a third z-axis that's pointing outwards, or it could rotate in any axis in between those coordinate axes. So it's not necessarily restricted to that axis. And what happens is, so to explain something as up, or so you can have one that's up or one that's down, is somewhat limited, you would think, in how many different ways an electron could be spinning. But this will all be explained in a bit here. The whole idea of this is a little bit hard to grasp, so I'm trying to cover all of the bases. So we'll just say for now, we'll accept for now that this electron has a spin of up or down. So there are two possible states of this electron. So the problem of alright, I have to explain something else before I get ahead of myself. So if you have a ring like this, I'll get black so it matches the wire we have. if you have a ring like this and you put it in, and so let's say that it has a magnetic field like this. Just imagine that all of the lines coming out of that ring are in that direction, and then you make a magnet here and a magnet here, so that all of the so that it's a field of magnetism. I'm going to make this blue so it stands out compared to the red one. So you get a magnetic field going from one magnet to the other, and this ring is suspended in this magnetic field. Now, the thing with magnets is they are attracted to each other based off of their polarity. So when you think of a ring in terms of a bar magnet, so if you had a magnet like this that had a plus and a minus, then a ring would be like a ring around this bar magnet, and so the plus end is where the arrows are pointing, in a sense. So the plus end would be here, and so I may have the magnetic field direction wrong, but let's say we have the plus up here and the minus down here. So this ring is kind of up. It's kind of pointed towards the plus end, but then since the way the arrow is pointing is the plus end here, when it comes to magnets, opposites attract. So the minus will attract the plus end, and the plus will attract the minus end. So what this ring will want to do is rotate this way and put itself in a state where it is as close to, where the plus end is as close to the minus end as possible, and the minus end is as close to the plus end as possible. And we'll imagine that it's perfectly in the middle, so it doesn't immediately fling to one side. It stays suspended, but it does rotate around its central axis so that it aligns with the magnetic field. And in order to do this, it requires work. So if you know anything about conservation of energy, there is no perpetual motion, there is no just random motion. Everything requires an equivalent amount of energy to occur. So I'm sorry about that. The motion of rotating this ring requires that a magnetic potential is great enough to do so. So this magnetic potential is somewhat like how if you want a ball to drop and hit the ground, that's the ground. If you want it to drop and hit the ground, then it needs to have a gravitational potential. So we say that's mg usually, and that's the force of no, that's the acceleration. Oh no, yeah, that's the force due to gravity on the particle. So because g is the acceleration. But a gravitational potential is just one type of potential. You can create a magnetic potential, and the way you create potentials is by putting energy in ahead of time. So the energy that caused this to be able to accelerate downwards was the initial energy of bringing the ball up to that place in the first place. So that doesn't necessarily have to happen at the same time. It could have been brought there a billion years ago, and then now it just drops. So that energy was put in, and then it was created into potential energy, and then the potential energy is converted back. So with this ring, a magnetic potential energy is created, and then the ring converts that magnetic potential into into kinetic energy and rotates to align with the magnetic field. Now this would be a small spike in order to do this, you would need, instead of having just a constant magnetic field, you'd have to spike the magnetic field, but the spike would be so minuscule that it would be relatively constant in terms of how that you would read on meters. So what happens in terms of electrons is when an electron rotates like this, or when a particle rotates like this, it has received energy, so now it has to spit that energy out. So what it does is, since an electron if we give it energy, it has to spit out energy, and what that energy is a photon. It's an electromagnetic wave. Well, it would be, a photon is part of an electromagnetic wave, or it's a difficult topic to explain. But so the electron, when it realigns with this magnetic field, it releases a photon. Now, the power of this photon, if we were talking about this ring that is at least somewhat macroscopic, the magnitude of that photon would be based off of this angle here. So we have this angle based off of how it is to the horizontal, and we'll say that's theta, because that's the main thing that is used for angles. So the photon, let's say that this ring would give off, would be the magnitude of it would be a function of this angle here. And what is weird when we deal with the quantum aspect of electrons, is that the photon is always the same magnitude. So you may say that's strange, and it is strange in terms of normal classical physics, but in terms of quantum physics, everything works out. So I will get to that in a second. So I'm going to let me see if there's anything I want to add on to in this picture. No, I'll clean the slate here. So bear with me. Alright. So, like I was saying, when you put an electron in a magnetic field, and we'll say that the magnetic field is going this way, and so then you put the magnetic potential in, the electron gains some energy, and in order to realign itself, it has to release this photon out. So what happens with quantum, in quantum mechanics, is that so the way that quantum mechanics makes up for the fact that this photon here is always the same magnitude is by it comes back to that idea of superposition. So we can't really see electrons, at least at the moment with our current technology. We can't visualize electrons. So because we can't observe them, we can't claim that they are rotating one way or another per se, unless we do experiments like the one I'm talking about. So when you put a electron in this field, then it will align with the field one way or another. And So if you had previously aligned it with this field that is over on an angle, let's say a 45-degree angle or something, so that's 45 degrees, then you move it to this, you move it from this field into this field over here. Then what happens is that instead of it being 100%, instead of you being 100% certain that this electron will align one way or the other based off of what spin it has to and then release a photon that is a function of this angle here of 45, instead of that being certain, you have a probability of the electron either firing a photon of the constant magnitude of electrons firing photons, or not firing a photon at all. And when an electron does fire the photon, then you know which way it is aligned. When it doesn't fire the photon, you know it is aligned in the opposite direction in terms of spin. And it's this probability that evens out the fact that the photon is constant. So if we imagine that you have a bunch of electrons in a big group, and you put them all in the first magnetic field and align them, and then you move them all to the second magnetic field, this probability will mean that only that probability of, or that percentage of electrons will fire the photons. And so then in total, on a macroscopic scale, the amount of energy that is released is a function of the angle. But the individual quantum-sized particles, the experience of them is a little harder to grasp your get your head around, because of this random probability of releasing this photon. So that is the general brush up on quantum, on the whole quantum aspect of electrons. And I'm sure I didn't give the best description of it. I can always explain more if you guys have any questions. So I'll try and summarize in general. So superposition means that you can't claim that it's one or the other. You have to claim that it is fluctuating constantly and infinitely between one and the other. So at any point in time it is both and none. And so a good application of this is, so let's say you have two slits, they're very close together, to where diffraction happens. And the diffraction is when light goes through, or when a particle goes through, when a particle goes through a slit that is very small, then it can diffract at an angle based off of how far apart those slits are. So then what the electrons do is, when you fire an electron at the two slits, then you must claim that, you must consider that the electron has gone through slit 1, you must consider that the electron has gone through slit 2, that it has gone through both slits, and that it has not gone through either of the slits. And so it is a superposition of all possibilities until you observe it And by observe it, in this case that I've shown, until you see that photon and you pick it up on a reader, you have to consider that it released a photon and it didn't release a photon, so that it is either up or down. But once you see the photon, then you know that the electron is in the orientation of a line that is aligned to be, I believe, up with the field. So that's superposition. So then the electron's spin is based off of the magnetic field created by a rotating charge, and the electron will align with a magnetic field based off of a probability of the angle to which it was originally aligned. Now, this experiment assumes that you have already figured out what direction the electron is aligned in, so you have primed it with this original direction. And then when you put it into, and the way you prime something, if you leave it long enough, it will align with the magnetic field. So then once the electron is primed, you can move it into the second the magnetic field, and it has a probability based off of this this degree of the angle to either fire off the photon or not. And then so it can switch between up and down with a random probability. So that's the general idea of the quantum aspect of an electron. And so I mentioned that I was going to talk about quantum entanglement, and so I will get a new slate here. And quantum entanglement is, you may be able to guess from the title, when you have more than one quantum particle interacting with each other. So let's say we have an electron, and let's say we have another electron. So this one's the red one, and this one is the blue one. And that's not normally the color you would color in electrons, but we've never seen them, so I'm going to call them red and blue. So we don't know about these electrons. Okay, so I can't say that. We've primed both of these electrons in the same magnetic field. So we know that they are both primed, and also we are claiming, and for explanation purposes, I'm not going to leave any gray area, these electrons are entangled. So I'm just going to draw this as a visualization. So let's say these two particles, electrons, are quantumly entangled, and so if we've primed them in the same magnetic field, then alone they should have the same probability of being up or down when placed in the new magnetic field. So I'm not going to draw all the arrows, but you guys get the picture. So if this entanglement were not here, then, like I said, with the group of electrons, these two would have, this one would have the probability based off of the angle of the priming magnetic field of being up or down, and this one would also have that probability, and they would be independent. So if this one was up and you knew that, it wouldn't change what this this particle is in terms of spin. So the difference with entanglement is that when you have electrons that are entangled, then let's say we know they're entangled, and then we keep this one here, and then we take this one over here and we put it in a box and we mail it all the way across the universe to a new solar system and give it to our friend that we know there somehow. So this electron is no longer here, it's in the box. So we're gonna put it over here. And we haven't done anything in terms of new magnetic fields, and we haven't allowed it to entangle with anything else. So now this one's in the box and we can't see it, and we give it to our friend. Then so we can do the normal experiment with this particle, and so if we do the normal experiment, then we turn on the magnetic field and we look for a photon. If we see the photon, then we're so I'm going to say that means the electron is spinning up. So if we see the photon, and we can say that this electron is spinning up, so we're going to say up. Then immediately, because these are entangled, and this is just the trait of entanglement, we know that the other electron is spinning down. And this is simply because they're entangled. I do not have the knowledge nor the capability to explain why this occurs, and I will shout out some videos at the end that might be able to give you some more insight on that. So if two particles are entangled and you measure one as up, then you know 100% certain that the other one is down. So even though this one over here in the box is all the way across the universe in a different solar system, in a different galaxy, in a different part of the universe, we know that this electron is up, so we know that the other one is down, and we don't even have to check it. But if our friend in the other universe, not in the other universe, in the if our friend that has the box, let's just forget the whole moving it far away, goes to measure this, we will know before they measure it that this one is down. And but in terms of probability, unless we if we call the person up and go tell the person, that's not a piece of poop, that's a phone, that our electron was up, then the probability is still the same for them, because there's no it's not they're not taking into account the results of the first electron. But if we call them, then they know that the probability is 100% of it happening. So this is the whole idea of quantum entanglement. And like I said, I'm not an expert in any way on this topic. I'm trying to just give a general overview of it. So there are some videos that are available to you if you want to learn more in terms of the more in-depth mathematics behind quantum entanglement. And those videos are out of Stanford. There's I believe there's almost a whole class of lectures on YouTube here that are completely open for you to go view, so I will post at least the first one in the description of the video after this is uploaded, and you can go check that out if you want to learn more. If you really want me to try and give a more in-depth description you can let me know about that either in the comments on this video or on Twitter. I'm not sure how much further I would be able to explain on this topic, but I am willing to give it my best and do some more personal research in order to give a better description to you guys if you truly wish to learn more. But I would recommend those videos, although I will say that they are relatively intensive in the terms of abstract math. So if you have trouble grasping some more abstract mathematical concepts, they may be a little bit out of your realm of preference in terms of learning, but they are interesting at the least. So like I said, I will put them in the description. So I've been talking for a while here. I'm going to put it to a commercial, and then I will do the normal segment that I've been doing on my Saturday streams, where I draw a random picture based off of random words. So I will be right back. In the meantime, enjoy a word from YouTube sponsors. Alright, I believe we are back from the ad. I know a lot of people have been claiming that those don't show up. I'm at least using them for a transition. So I mean, if you can still hear me, I understand that if you can still hear me during the ad, I can understand that. I understand that occurs, so I don't really need to be notified about that. I think it's just the fact that at the moment I don't have the largest audience, so when I request an ad I don't always get one. But that being aside, I will move on to my next segment. So the segment is the normal segment I do on the Saturday streams. So I have my paper here. I'm going to generate 3 random numbers. So I have 7, that's a car. I have 22, which for the verb is digest. This will be interesting. And I have 10 for the adjective is super. So we have to first decide whether the car is super or the digestion is super, but we can just assume that both of them are super. A superposition of superness, of digestion, and automobile mayhem. So first, let's get a car going. So we're going to do our normal boxy urban sedan. We'll get the normal wheels going. They are very small compared to the car. But you know, we're not really considering fuel economy when we are drawing this car, because we understand that this car is going to digest something, and what better to digest than what better car at digesting than a gas guzzling behemoth. So we have a 4-door sedan with a rear view mirror, and then the window and the rear window, and that is not the prettiest thing, but we'll give it some headlights, and we're gonna get the light coming out here. And then if it's super, I mean, we'll probably give it a cape. I'm just going to hang it off the back here because that seems the best in terms of aerodynamics. So we'll get the cape going. Kind of looks like a tongue, but I'll try to add some detail in here. So then give it the seal of approval. It's the it is super. So there's a supercar, and if it's super, we can assume it's going fairly fast. We could even assume that it is flying by some sort of mental power of anti-gravity. And so if the car is digesting something, it would have to have some sort of acidic stomach. So we can, if we have the fuel tank cap back here, so that's the door, and then you have the fuel intake, and that is colored in. So we're gonna take a hamburger, and we are going to finish drawing the hamburger without ruining the burger itself. And then if the car were to digest it, I personally would assume that we would want to just shove the hamburger into the fuel pipe and then let it sit in the fumes for a while. But well, let's assume that this is a relatively acidic fuel, so the whole process of taking in the hamburger into the engine and then exploding the hamburger in the piston and then pumping and pumping, and finally the exhaust would be back here and the hamburger would come out and add to this trail of wind from how fast it's going. So I think that a car wouldn't have too much trouble of dismantling the burger, but in terms of turning it into a fuel, I think that a normal car would have a lot of trouble digesting. So we'll assume that this is just another trait of the superiority of the car. So this car has a reservoir of acidic of let's just imagine that it's a bucket. So there's this bucket in here and it's got acid in here, and somehow through chemical magic, which magic is okay because we're talking about a supercar, the burger will bubble through and turn into a flammable fuel that it would be preferably liquid that could go into the engine and begin the combustion process in order to propel the car forward. But I question whether the car needs to digest this food because it can already fly and move really fast. So unless this gas is required for the anti-gravity devices in the wheels, I would assume that the whole aspect of digestion would be somewhat irrelevant. But you know, supercars have to have hobbies, and if eating burgers is a hobby of the supercar, I will not judge it in the least. So I'm just going to add some clouds up here for aesthetic, and the sun to make it look even more like a child's drawing of a small urban sedan. And I will consider that a finished product. So I want to thank you all for sticking with me if you did, and if you're watching this later on YouTube, Please feel free to subscribe and follow me on Twitter. My Twitter account is Jono Explains. That's Jono Explains without the things. And then, like I said, on Wednesday I will be at the ASME Makers Fair. I believe they call it a showcase, to show off my AI in the engineering atrium of the UCF campus. So if you are on campus on Tuesday, I believe that showcase is from 12 to 2. I wouldn't quote me on that exactly, but at least is going on at some point between 12 and 2. So I will be out there. If you want to come hang out, ask me questions in person. But that being said, I am going to sign off. So I thank you for watching, and I will see you on Wednesday.